So today I'm going to deliver the lecture on one of the biomedical signal processing, which is an ECG signal. So this ECG signal classification and an ultra low power microcontroller implementation. This is the latest IEEE transaction paper, ECG arrhythmia classification and ultra low power microcontroller by Remy. With due acknowledgement to this author, will proceed for the further implementation of this ECG classification. Um, so as far as the ECG signals are concerned, it's really a challenging one. The challenging part is that they are less in amplitude. The ECG amplitude or the EEG or EOG. So all these are biomedical signals. They have very low amplitude. For example, if you take ECG, the amplitude will be in the range of from milli volts to say microvolts per EEG and so on. So while taking the ECG of a person, generally normally will use the electrodes. So that causes a lot of noise addition to the original ECG signal. So pre-processing of these signals is to be done. And then these need to be implemented in a real-time platform. So the wearable biomedical systems, they allow doctors to continuously monitor the patients over longer periods, which is especially useful to detect rarely occurring events such as cardiac arrhythmias. So the work first to document a complete beat-to-beat arrhythmia classification system based on custom ultra low power microcontroller. Though here I am saying ultra low power microcontroller, the same can be implemented using a FPGA, a field programmable gate array, or it can be done on an ASIC. So that's the reason why I have chosen this topic, so that the same experimentation can be extended for the FPGA, or it can be done on an ASIC. So that is what the idea. So it includes a single channel analog front end circuit for acquiring the ECG signal, and also there will be a digital backend processor to execute support vector machine. The SVM is particularly, as you all know, this is used for the disease classification, and particularly the others has taken ARM Cortex CPU. So nowadays we are well equipped with latest kind of FPGAs like Zinc or JUT boards with all accessories and the peripheral access. So in your VLSI implementation, you may replace this particular ARM Cortex processor with either FPGA, or we may have a ASIC implementation also. So that is the idea of taking this particular topic. So let us look at why should I go for the VLSI implementation, or a microcontroller, or embedded processor, or FPGA implementations. See, if I take a software a simulation kind of environment like MATLAB, my job will be more easy, as the MATLAB contains built-in functions for implementation. Then it will be quite easy for me. But if I want to have a handheld device or a wearable device that can help the doctors, or very easy access if I need, so I should go for the hardware implementation. So let us look at what that makes the hardware implementation special. Is, you can observe, if I implement this on a software, the software implementation is sequential in nature. That means after executing the first instruction, then the second instruction need to be executed, and so on. And whereas when it comes to the hardware, it's concurrent in nature, so which makes the hardware implementation much faster and robust when compared with the software implementation. Similarly, the software implementation is more error prone, whereas the hardware implementation is robust in nature. For software implementation, you require the programming knowledge. Like if I want to implement in MATLAB, I should be knowing what are all the built-in functions. If it is required, I need to write the user-defined function. But when it comes to the hardware, you require the design aspects. Like you need to design a data acquisition system, or you should use the processor for converting the analog signal into a digital signal. A to D converter need to be implemented, and for example, you need a VLSI architecture for denoising of your biomedical signal, all that. So you require the design skills if you want to implement it on the hardware. When it comes to the software, it's a low cost, as most of the open source softwares, they are available free of cost. But when it comes to the hardware implementation, we need to buy, whether it is an FPGA or an embedded processor, an embedded controller, you have to buy it. So there will be a significant cost involved in the hardware implementation. When it comes to the software implementation, there are well-defined and well-developed programming methods, whereas the hardware prototypes, they are very hard to build. Just whatever we have discussed, you can observe that the running speed of the software implementation is it is computationally costly and time consuming. So the software system may not be sufficient and satisfactory when the real-time application is needed. So on-chip hardware implementation is necessary for real-time applications. So nowadays, what the people are doing is hardware and software implementation are commonly used in different fields of applications. So we use a combination of both software and hardware. And also the amount of software implementation, it is widely prevalent. There is an integrated implementation methodology, which is a hybrid software and hardware approach. So software approach and hardware approach combined, we can have a hybrid approach that will benefit from the software learning capabilities in the aim to attain an efficient real-time hardware. So you may better to have a FPGA implementation. See, why we can prefer FPGA is FPGA, as you know, they are reprogrammable and reconfigurable. See, whenever I want to have a reprogrammability or reconfigurable flexibility, better I may go for FPGA implementation. If the functionality is fixed and I don't want to reconfigure or reprogram the processor, then I may choose the ASIC implementation as application specific integrated circuit implementation. So for instance, most systems are developed and implemented in software when the particular task does not require much speed. So the hardware implementation is necessary for time consuming application, and they find more importance in real time constraints. So when it comes to the real time systems, what is meant by real time system is execution of any application with timing constraints. You can divide the this real-time systems into a hard real-time system and soft real-time systems. So for what is a hard time real-time system and soft real-time system? Let us look at. So one example for this one, hard real-time system, digital fly-by-wire control system in an aircraft. See, in an aircraft, the timing constraints are tightly bound, and you cannot have a delay. So no delay is accepted Otherwise, the lives of people depend on the correct working of the control system of an aircraft, because more and more number of passengers will be traveling through the aircraft. If any real-time constraint was not met, there will be a fatality of these people. So that's an example for a hard real-time system. When it comes to the soft real-time system, you can take an example of a soft drink vending machine, where where I deposit an amount, the soft drink vending machine will be dispensing the required soft drink. So there, even some time delay can be accepted, and there won't be any catastrophic effect, even though the deadlines are not met. Of course, when of course the person, the consumer will wait for a couple of extra minutes or so. But when it comes to the hard real-time system, they are tightly time bound, and there is no delay acceptance. So this is what the real-time system. So you can have a real-time system implementation of a device that can help the physician to diagnose the patient, and and analyze with what kind of heart anomaly he is suffering or so. So there are CVD, which is cardiovascular disease. They are the leading cause of death and disability worldwide, especially in developed country. Among those, cardiac arrhythmias are associated with an increased risk of stroke and sudden cardiac death. In order to diagnose the heart disease, one of the most effective tools in the ECG, which measures the electrical activity of the heart. This is what an ECG is. And however, due to the infrequent nature of arrhythmia events, long-term monitoring using wearable device is often necessary to observe them. So we will use a monitoring device during the patient's daily activities, impose stringent requirements on the signal quality, as well as size and also power consumption. To avoid the need for transmitting or storing very large amounts of data, real-time processing of the signal to detect the cardiac arrhythmia has emerged as a solution to extract only the relevant information when abnormal event occurs. So this is what the brief introduction about the cardiovascular disease. And you can observe that when I want to develop a continuous monitoring device, so I should focus on the stringent requirements of how the signal quality is. So what is the size, and how much power consumption is being made. These are the important constraints that I need to consider. And this is what, if I want to do, as we discussed just now, if I want to do any hardware implementation, first of all, I need to have a system architecture. So here in the figure shows the system architecture of the sleep rider SOC for arrhythmia classification. The top schematic, it illustrates the hardware components of system on chip. So it can be just here we said that it's like a ARM processor microcontroller. The same can be done on an FPGA, as I am repeatedly saying the same thing. So just we'll replace it with instead of a high-end microcontroller or a microprocessor, we will replace that with an FPGA. And for the FPGA implementation, we have beautiful. So though I'm not a hardware description language HDL expert, if I am good at the architecture of this, there is a beautiful tool in Xilinx, and as well as MATLAB has a connectivity system generator tool is there. I may use that system generator tool. Just it is like a block diagram level entry, which I can use, and then make my system generator model, simulate, then synthesize, and I can program my FPGA with a dot bit file or a dot hex file. So that makes my implementation much easier. So I need not struggle with either Verilog HDL coding or VHDL coding. That's the okay. That is an easily available option, system generator. So you may try for that. For implementing that system generator, this one basically I need an architecture. You can see the architecture that was shown here. So the first figure A, it's like hardware implementation. There you have the ECG signal, which is analog in nature, and then that analog front end portion contains the bias generation and other things, and there is an A to D converter which converts the biomedical analog signal into a digital signal, as you are very much aware. So conversion of the analog signal into a digital, so the digital signal is immune to noise, so that the digital signal will not get affected much with noise. So that is the reason why I'll use most of the biomedical signal processing applications and other things after pre-processing. There is an ADC. Then in the digital domain, we are going to process the signal. In the digital backend, we have ARM Cortex M4, so which I can replace with a FPGA or so. And then there is a static RAM. There are two kinds of static RAMs. One is exclusively for the data. Other one is for the program memory. There is a direct memory access. DMA is there. So there is a clock and power management unit with low voltage supply generation, and there is a clock reference and current reference is there. So when it comes to the block diagram of offline training process, yeah, here we have an embedded software loop, and for classification purpose, we are making use of a, as we said, support vector machine, SVM classification, where the blue color highlights the ECG signal input and the output inferred beat classes. So N for normal beats, S for supraventricular, and V for ventricular arrhythmia. See, arrhythmia is a kind of anomaly, heart anomaly. Normal, as we all know that there is no anomaly, but whereas when it comes to S or V, they are the anomalies, particularly here arrhythmia anomalies we are referring. So the system architecture, let us look at the system architecture. The ECG arrhythmia classification system is embedded in the Sleep Rider microcontroller unit, MCU SoC, which is shown here in figure A. So this is what we are seeing, Sleep Rider SoC. And pair of chest electrodes are connected to the different inputs of the instrumentation amplifier in the AFE. So the third electrode is used to set the patient reference voltage through an on-chip buffer. And the instrumentation amplifier uses a current balancing topology with chopper modulation. And the differential output of the instrumentation amplifier is digitized at 250 edges using single-ended time-based ADCs, which we are shown here, A to D converter. So this IA refers to an instrumentation amplifier. As we already discussed, the amplitude of this ECG signal is so low that for the processing purpose, it's very difficult to process such a low amplitude signal. That's why you make use of a instrumentation amplifier. That is the purpose of this instrumentation, which amplifies that very low amplitude signal, ECG signal, and with 14-bit resolution. The acquired samples, they are temporarily stored in the static RAM. So SRAM here, we have shown two SRAMs of 48 KB size. One is for program memory, another one is for data memory. And the acquired samples, they are temporarily stored in the static RAM and by the different memory access module while the system is in sleep mode, and your DB is inactive. And 128 samples have been stored in the memory. The ARM Cortex processor inside the DB wake up and it processes the data. See, why we are keeping that in sleep mode is because to have low power consumption, unnecessary power utilization by the processor is to be avoided. So we'll keep it in say sleep, and then once um, it is done, the DB will wake up and process the data. So a clock and power management unit, it provides the reference current, low frequency peripheral clock at 4 megahertz and a high frequency clock at 64 megahertz. Several low voltage supplies for the different blocks are there also shown, and they are also shown here. And the blocks which are also, they'll generate 1.8 volt supply, zero point 0.4 volts for ADC, and the digital logic, 0.5 volts and 0.8 volts for the memories and auxiliary blocks. You can see multiple voltages are being used. For ADC, the voltage that is being used is 0.4 volts, and 0.5 volts and 0.8 volts for the memory units and the auxiliary blocks. So in the analog front end, we have seen there is a LNA. LNA is nothing but a low noise amplifier. So we are the fully differential current balancing topology of the instrumentation amplifier. It is shown here. So this instrumentation amplifier circuit in in the blue, the inputs VN are connected to an off-chip high-pass filter, and the output are connected to the analog to digital converter. The DC bias voltage, they are generated by bias generation circuit from the reference current, which are originating from the power management unit. You can see the current balancing topology of the instrumentation amplifier. So you observe that various mass transistors, both NMOS and PMOS, are being shown. So hence it is a CMOS kind of implementation. So the fully differential current balancing topology of the instrumentation amplifier we have shown. This relies on transconductance GM and trans impedance stage. You can observe that we said IA, in that we have shown instrumentation amplifier. We have indicated GM and ZM, where GM being a transconductance and ZM being trans impedance stage. So why these stages? In the GM stage, the input differential voltage, it is copied by the flipped voltage follower structure with transistors P1 and P2 across resistance Ri. So you can observe that we have the here we have the transistors, like this is your P1 and the P2 transistors are there. So you can observe that with transistor P1 and P2 across resistance Ri, here you observe that Ri is the resistance, and the flipped voltage follower, it provides FVF is short form for flipped voltage follower. It provides a unity gain, large input range. Also, it acts as a current sensor. The P3, P5 structure, it has the lower drain voltage of P1, and also it improves the input dynamic range of the instrumentation amplifier. So the adjacent figure 3, which shows the power noise trade-off in the instrumentation amplifier, in which optimal points represent a set of sizing parameters obtained by the generic algorithm. The dotted line shows the constraint PEF contours at a particular supply voltage of 1.8, which you can see in the plot. Okay, the current difference is copied to the ZM stage, which we will say a trans impedance stage using P2 P6 current mirrors. So here P2 P6 current mirrors are shown clearly in the instrumentation amplifier circuit. with the current gain A and goes through the resistor R0 to generate a differential voltage. So we can calculate the transconductance GM using making use of this equation. We said that GM is transconductance. Here you can observe transconductance, and trans impedance is represented by Zm. So Zm is equal to R0. Of course, this is very simple, whereas GM is given by this equation. So how do you calculate the voltage gain? Is you have, if you have the knowledge of GM and as well as Zm, GM into A into Zm gives you this gain. And there is a, you can observe in the architecture, there is a time-based analog to digital converter. The differential signal at the output of the instrumentation amplifier is digitized by two single-ended time-based analog to digital converters, which are shown in figure 5. A voltage controlled oscillators, we can use a VCRO or simply so VCO is voltage controlled oscillator. Here, as there is a, we are using a ring oscillator, we are saying VCRO, voltage controlled ring oscillator, which performs the voltage to time domain conversion. The phase of oscillator is integrated by the counter, and successive samples from the counter, they are differentiated to obtain the frequency information. So why should we use this time-based ADCs? There are advantages associated with it. Or implemented as a digital only modules using foundry standstill results in a limited design effort and low area. So the two major advantages being, one is the limited design effort and low area. That's what the advantage that you get. The main bottleneck of this voltage controlled ring oscillator based ADC is the non-linearity of voltage to frequency conversion. There is a voltage to frequency conversion. During that process, you will get a non-linear curve. So a typical current starred ring oscillator has a strongly non-linear transfer function, which strongly limits the input, of course, input dynamic range. Previous works which they have dealt this issue by adding a feedback loop to reduce the input swing of the signal. So in this research work, the author has taken the advantage of strong back gate effect in FD SY technologies to create a back bias controlled oscillator, which is abbreviated as BBCO, which offers much larger input dynamic range, and significantly it improves the linearity. And also they have taken a back gate bias to the input voltage of the ADC. The threshold voltage of the transistor VTH can be reduced, which changes the current in each stage and the frequency of the ring oscillator. So ST Microelectronics is the vendor which who gives 28 nanometer FDSY technology is used in this particular research work by the authors, which will offer different voltage threshold options that can be operated in forward back biasing for LVT transistors, or reverse biasing. That is reverse back biasing is simply abbreviated as RBB for RVT transistors. And if you observe, there are PMOS and NMOS. LVT, PMOS and RVT NMOS device will result in negative back bias voltages, whereas LVT NMOS and RVT PMOS will have a positive back bias voltage. And the input voltage range, you observe that it is like 0 to 1.8 volts only. And only the LVT NMOS and the RVT PMOS backstage gates can be driven, while the other transistors are kept at their nominal back gate voltage. So this is what we can observe. And finally, the resolution of and quantization noise of ADC, they are set by frequency of the BBCO, as we have already seen here. Back bias controlled oscillator, which depends on number of stages and the sampling frequency. So a smaller BBCO with higher frequency, it will improve the resolution but increases the power consumption. And we need to make the front end design is over. We need to do the digital back end design. The data samples, they are retrieved from the AFE, are processed sequentially in the DBE. And so those who are working in the ECG signal processing, they are very much aware about the QRS complex of the ECG signal. Let us look at this QRS complex signal. The ECG arrhythmia example, in figure 9, you can see, okay, this is what the QRS complex signal. So, this in the ECG. So first the heartbeats, they are detected. A very famous algorithm that all the biomedical ECG signal processing people use is Pan and Tompkin algorithm, which consists in a band pass filter, a derivation, a moving average and adaptive threshold. And this allows to detect the sharp peaks in the signal that likely correspond to the QRS complexes of the ECG signal, which just now we have seen that QRS complex. This is a QRS complex, and you have the supraventricular beat, which is S, which is characterized by its prematurity and the lack of P wave, which is masked. The ventricular beat is characterized by prematurity and broad irregularity QRS complex signal. So you can observe the plot of voltage, which is indicated in on the y-axis. We have millivolts amplitude of this ECG signal, and time in seconds on the x-axis. So one is S, which is supraventricular beat, and you have V, ventricular beat. So and you have the QRS complex, broad irregularity is shown here in QRS complex is shown here. So which we are referring as figure. When we are using a microcontroller unit, an MCU, as a basis for arrhythmia classification system, the detection classification algorithm is programmed in the SRAM and executed in software. So instead of the microcontroller unit, as I said, we can have a as well as an FPGA. The algorithm designed within the feature selection process and the SVM classifier, support vector machine, hardware implementation of DB, and the real-time execution constraints. The three classes considered in this research work are normal heartbeats with sinus rhythm, which are said to be N, and supraventricular beats, which are S, and ventricular beats, which are V. So the examples for the normal, for the supraventricular and as well as ventricular are shown here, S, V, and N for normal. And so there are different types of arrhythmia, which shows disruption in the normal sinus rhythm. Their characteristics are quite different. The V beats differ mostly by the shape of their QRS complex. So as we said here, this is ventricular beats. They will generally differ mostly by the shape of QRS complex. The shape of this QRS complex is different from supra, okay, ventricular. So you can observe that these beats are completely different from the okay, ventricular beats. So the S beats are morphologically close to the N beats with only a missing P wave, which is often hard to observe in the baseline noise. For classification purpose, the feature used to beat distinguish the classes must therefore different in each case, which rarely done using traditional 1 against to other SVM classifier. So you have different intervals. You may say RR, that is beat to beat interval. RR average, that is average of last 20 RR intervals. difference between local intervals, and there is uh, PQRS. So generally, your ECG signal is classified as this PQRS and QRS complex. We have already seen, and you have a discrete wavelet transform DWT, and the decomposition of that with the different levels like DWT decomposition level 2, level 3, level 4, they are shown particularly here. And yeah, you have number of features before and after the selections are highlighted in this particular table. You can observe. We'll take a support vector machine classifier. The feature selection process is performed by a sequential forward and floating search algorithm, which iteratively adds or removes the features from the set based on the improvement of the cross validation interference program. This performance is measured by the J index equal to the mean of the sensitiveness, which is said as SEN, and positive predict value, which is PPV. Then there is the corresponding equation. The arbitrary figure of merit is normalized to 100%, avoid the bias due to large portion of n number of beats. And here the authors has shown the performance evolution with number of features, where it can be observed that a low number of features below 10 is already sufficient to achieve the peak performance. So you can have the selected feature types which are different for each classifier, which are shown in the table 1. This is table 1, which we already have seen. Despite the feature selection, a significant overlap between classes is still present due to interpolation variability for the two most discriminative features in the classifiers. And when you want to do the hardware implementation and the real-time execution, here is, as we already the software implementation as hardware implementation being based on the concurrent nature. The software execution is performed on ARM Cortex CPU in order to minimize the energy required for performing the task. Ultra low power implementation techniques will be used, and the CPU logic operates at the ultra low voltage of 0.54 volt to reduce its power consumption at the expense of reduced clock frequency and increased sensitivity to various PVT variations. So there is a sleep rider chip, micro photograph, and AFE layout. They are shown here. And there is the system measurement setup with the custom test PCB is also shown. So what is very much required is that if I want to implement the same on an FPGA, how I can go for the same kind of ECG detection and arrhythmia classification using FPGA. Let me stop this and switch over to the FPGA implementation. See, this I have shown you how the classification is done based on the microcontroller, like ARM microcontroller. See, the same task can be performed using your FPGA implementation, which makes the VLSI implementation very easy when compared with the other implementation. As I told you that we can just make use of a system generator tool. So let me share the presentation where we talk about the particularly the FPG implementation portion. Just let me share that presentation so that we can discuss how the same can be implemented, making use of an FPGA. Yeah. Is the screen visible? Presentation?
Yes, sir.
Yeah. So FPG based system for heart rate monitoring is this is what we can do. So we already seen this is what the basics of ECG or electrocardiogram. So you can we said that QRS complex and other things. So here you have a clear clarity of what is a QRS complex. You can observe that the amplitude of it being 1 millivolt and the duration in milliseconds. Particularly, you observe for the fourth item where you can see that there is a QRS complex, so which I am highlighting. So this has an amplitude of 1 and the duration of which is 80 to 120 milliseconds. Similarly, you can see there is a segment called PR segment and SR segment. This is how a typical ECG waveform will look like, and with various QRS complex and PR segment and ST segment and corresponding PR intervals and QT intervals are highlighted here. So this is what the recording of the activity. So we said that what we previously we have seen, we said that arrhythmia. So what is it? An arrhythmia, it describes an irregular heartbeat. The heart may beat too fast or too slowly, or it may beat even too early or irregularly. See, all the four scenario are abnormalities only. But when we will say there are two various types like left bundle branch block. When do we say LBB, left bundle QRS duration is greater than 120 milliseconds, and there is an absence of Q wave, then we will say it's an anomaly called LBB. Similarly, right bundle branch block is again another anomaly. Okay, and preventricular PVC, so paced. Like this, these are all various kind of cardiac arrhythmia, and based on the type of beats, their features are shown here. So when I want to do the so ECG signal classification, first of all I will take an ECG signal, and then we will do the pre-processing of this ECG signal, and the next step is I'll do the feature extraction, then the beat classification. Like we have seen in earlier case, normal, there we said supraventricular and ventricular, whereas here the classification we are taking is normal. Anyway, in earlier case also we have seen that, and of course apart from N, V, and S, we have taken here LBB, left bundle branch block, and right bundle branch block. These are different kinds of beats, the type of beats, and in various cardiac arrhythmia that we are talking about. Okay, now The diagnosis system generates different parameters for different diseases that are dynamic in nature and to be programmed parallel in real time. These are achieved using FPGA. So the FPGA is dynamically configurable. We said that reconfigurable. Parallel execution is again another advantage. Less computing power compared to a digital signal processing. All these makes the FPGA implementation as a good choice for the biomedical signal processing application. Time to market by testing an idea or concept and verify it in hardware without going through the long fabrication process of ASIC design. You may go for FPGA implementation. So this work you can present it on a FPGA. So the architecture, you can use a Nexus for FPGA evolution kit or any other. As I said, you may use the latest FPGA Jink or JUD board also can be taken, and all the data related to this arrhythmia classification are taken from the standard database by the authors. So with due acknowledgement to these authors, this is what the FPGA-based system for heart rate monitoring, which is an standard transaction paper that was taken. And yeah, so for various algorithms that are developed in software to detect QRS complex in ECG signal, reflects the great advances in signal processing. However, these are many other approaches, such as you have genetic algorithm approach and heuristic method, Hilbert transform, and empirical mode decomposition. So hardware implementation using FPGA chip has become one of the most used recent technologies. So that's the reason why you can go for FPGA implementation. We said that the earlier paper also, they have used the Pon-Tompkins QRS detection algorithm, which is implemented on FPGA using Verilog hardware description language. So here the authors has used Verilog hardware description language instead of the Verilog hardware description language. You can as well go for, as I said, that you may use it for using a system generator implementation also can be done. So it is this is used using Xilinx system generator. Okay, so let me go for that. So you have an ECG signal. Okay, and we have seen P, T, Q, and QRS complex. The ECG signal is mostly generated by detecting and amplifying a small potential changes, potential charges on the skin. So that's the reason why you'll get the ECG signal amplitude in millivolts. These changes are activated when the electrical signal in the heart muscle changes and spreads during each heartbeat. They appear as small rises and falls in the voltage between two electrodes placed at either side of the heart. To design and validate the system for detection of QRS complex, the authors have used the database of MIT BAH, as we have already seen this. Okay, and the records were digitized at 360 hertz and bandpass filtered in this frequency range with a resolution of 11 bits over a range of 10 millivolts. To validate the proposed embedded system, several electronic modules are used. The EC signal was acquired with 3 electrodes. So this electronic module was modified to analyze its frequency band up to 120 hertz while adding a 50 hertz notch filter to reject the power line interference. Normally, when you are dealing with biomedical signals, especially with the ECG signal, you will get the power line interference. In order to read that power line interference, we can use a 50 hertz notch filter. The resulting analog signal from the conditional circuit is passed through analog to digital converter. The same thing which we have discussed earlier in the implementation on an ultra low power microcontroller like ARM Cortex M processor. Here we are implementing the same thing on an FPGA. And this is what the diagram of embedded system that was proposed by authors. So there is a ECG signal which was acquired, and then from the ECG module, whatever the ECG signal that is acquired will be given to an analog to digital converter, and then it will be given to a FPGA, which is here particularly the authors has taken a Nexus 4 FPGA board. And there is again another, as the after processing making use of the FPGA, then your a digital signal need to be converted into analog signal, and then it is given to an analog discovery board, and then to a waveform interface so that we can analyze and with which particular anomaly the particular patient or the subject is suffering. So this QRS detection algorithm has two main stages. Pre-processing stage, I already told you that for removal of noise, we will use this pre-processing stage. In this pre-processing stage, there are 5 consecutive filters, and the next main stage is R-peak detection stage, which itself is composed of 3 parts, taking the center derivative, detecting the maximum peak, and thresholding on the amplitude and time. These are shown in this figure. So we have this procedure of the proposed algorithm. In the pre-processing stage, we said that 5 filters signal, the acquired ECG signal is passed through a band pass filter, then there is a derivative filter, there is a squaring operation, there is an integrator filter, and then low pass filter. So 5 stages you can observe, 1, 2, 3, 4, and 5 stages during the pre-processing, which removes the noise from the ECG signal. And after pre-processing, it is given to a QRS detection stage, where the first block being center derivative. After pre-processing, the after removal of the noise from the ECG signal, it is given to a center derivative. Then there will be a maximum peak detector. Then there is an adaptive thresholding. Then the heart rate calculation and the heart rate display is shown here. And here, after the calculation of the heart rate, so you are able to detect which kind of arrhythmia it is. So we already discussed that the arrhythmia types are cardiac arrhythmias, are myocardial infraction, okay, AF, which is atrial fibrillation, and cardiomyopathy, and ventricular fibrillation. So these are the 4 kinds of cardiac arrhythmias that we are going to decide which kind of arrhythmia it is. That's what the meaning of this arrhythmia detection here, this block, as we already seen, QRS detection stage. And during the ECG pre-processing stage, as you observe that there are different kinds of filters. The ECG signal, first stage is mainly based on, we said that in the earlier microcontroller based implementation also, we said Pan and Tumpkin algorithm, and here also we have taken the same algorithm for in the FPGA implementation with the addition of low pass filter to better smooth is its output. Therefore, ECG signal is first band pass filtered in the range of 5 to 15 hertz using both using a 4th order recursive filter. So this is a 4th order recursive filter that you can see. So the corresponding these equations are given, 4th order recursive filter, and the QRS complex detection for the, as we have seen in this stage, there is a centered derivative. You observe centered derivative, and corresponding centered derivative equation is given here. and then maximum peak detection. So how we detect? You observe that we'll calculate this center derivative d of n equation. If d of n with d of n minus 1, if it is less than 0, we'll say s peak. Okay, zero crossing. To detect the peaks, the zero crossing of the derivative of the pre-processed ECG are calculated using intermediate value theorem, and this is what the equations that are used. So we may use adaptive thresholds, which are used to, because amplitude of the beats can vary significantly from one recording to another recording. So so this is what the top level implementation of QRS complex detection. As I said, this is a Xilinx system generator. So the basic requirements in your system, you must have a Xilinx Vivado software compatible with a MATLAB version, and in the system generator. So if that is successful, then you can have a block diagram level. In block diagram level kind of design. Here, all these are blocks. So this is a Xilinx system generator. So this is your ECG input, and the gateway that takes the input, and this is a pre-processing and peak detection and arrhythmia detection stages. Now we can, this is top level. That means in pre-processing, what should be there? The pre-processing stage should contain 5 different stages we already discussed. So the pre-processing 5 different stages. What are the 5 different stages are? First one is the low pass filter. Second one is the derivative filter, and this is a multiplier. This is an integrator block, and this is a low pass filter. See that again, this low pass filter need to be built. This is again a top level block diagram. Inside this, you should have a low pass filter, this one equation and other things. The derivative block will be created making use of this derivative equation. Okay, and similarly for this low pass filtered equation or a band pass filtered equation will be there inside this this one. And similarly, of course, multiplier. These are like drag and drop kind of blocks in the Xilinx system generator. You can make use of these built-in multiplier, and of course integrator, and then low pass filter, then the output. See, after doing this, you can have a QRS detection blocks. The Xilinx system implementation of, if you want to implement the band pass filter, see, it's a 4th order filter. So in your Xilinx system generator, this is an adder. So you can just use an adder block. You can drag, drop, and connect. Then you need a multiplier. You need a delay element. Z inverse, what the Z inverse indicates? It's a delay element. So you can use a delay element. So you yourself can make use of this block diagram level entry, that is a system generator block set, and you can comfortably implement this particular system generator. So it's particularly implementation of the band pass filter of system generator. XSG means system generator, Xilinx system generator block set. Similarly, the second stage, see, you observe that this is your top level block. Inside that, you have this system generator blocks. Like I said, that derivative block. So there is the derivative block here. The derivative, inside this derivative block, you have this Xilinx system generator model, which I am showing here. So you can use this Xilinx system generator blocks. So just you See, I need not be a HDL expert. See, just if I know the architecture, and then if I know the say Xilinx system generator blocks, the appropriate blocks, and if the architecture is known to me, then implementation becomes so easy for me. Then here, implementation of the integrator filter. This is an implementation of an integrator filter. The various delay elements here, first delay, delay 2, delay 3, and so on, you observe. We said, okay, 54 delays you observe. So here, that's the reason why starting from delay 1 to delay 53, we have 54 delay elements. And there are adder, come, subtractor, add, sub. Okay, these are number of adders and subtractor blocks that you can observe, and all these two outputs of the adder blocks, chain of adder blocks, and this chain of delay elements output is connected to again an adder come subtractor, and then we are going to get the output of that integrator filter. And how do you implement a low pass filter is you require an adder subtractor block. You need a C multiply, means I am constant multiplier. See, I am multiplying with a constant. See, when I require this is if my coefficient value is 0.9827 into x of n minus 1. X of n is the input, and x of n delayed by 1 unit is x of n minus 1. See, 0.9827 into x of n minus 1 is my equation. So how do I implement the same using the Xilinx system generator is just make use of a constant multiplier block with a value of 0.9827, and to that you give x of n minus 1 as an input. So x of n minus 1 gets multiplied with this 0.9827. That's it. So x of n is my input. See, you observe here. This is given to a delay element. The output is delayed by 1 unit, and the same is multiplied with a constant multiplier. So on either side of this, we have two multiplier units, constant multiplier 1 and constant multiplier 2. See, after multiplying the delayed value x of n minus 1 with the constant multiplier, they are given to an adder come subtractor block a plus b, which is a addition. Here one input is a, another input is b. Output is the addition of these two. That's it. So this is overall QRS detection block implementation. So you can try this Xilinx system generator implementation. So I think I have done this same implemented using Xilinx system generator block, and yeah, so yeah, this results in a okay, instead of these results which are given in this, we have done a Xilinx system generator implementation. I want to show those waveforms making use of the Xilinx system generator block. Let me stop sharing this so that I can show that the implementation that were done making use of the Xilinx system generator. See, even the same, we can extend it for other biomedical signals, like even for EOG also, electrooculography. See, we have done, see, because the authors has done for ECG, we have extended it for EOG signals also, electrooculography. And FAR filter architecture was taken. So, is the presentation visible?
Yes, sir.
Yeah. So just an example I have taken is the EOG signal, electrooculography, instead of ECG. So digital FIR filter implementation was clearly shown here. So we have a FIR filter coefficients shown here, and then the FIR filter architecture. It's quite known for everyone. And the same FIR filter implementation is done using Xilinx system generator. So we have a gateway in, this is input, and there is a scope that gives you the waveforms of, in the Xilinx system generator, there is a scope block, just like the oscilloscope that we use in laboratories. Similar kind of simulator oscilloscope is available for us. So this is FAR filter subsystem module that we have implemented, and this is a noisy EOG signal, and the denoised EOG signal is shown. The same we have extended for EOG signal also, and this is what we can say. And also we can have a kind of Xilinx system generator blocks also, like XSG, so Xilinx system generator blocks. So you can have a FIR SLX kind of this thing. See, if you have a system generator, so you need to first of all open the MATLAB environment having the compatibility with the system generator, and then you can work out. And you should ensure that both the Xilinx Vivado version, MATLAB version, they are compatible to have a system generator, system generator feature, so that you can try to implement the same on the FPGA using Xilinx system generator feature. So with this, maybe I can say I can conclude this. So with the due acknowledgement for the authors that they have done the implementations on microcontroller or FPGA, but we have extended the same for other kind of biomedical images like EOG and other things. So the same manner, if any research scholars are working on the VLSI implementations, they can take this easy and beautiful feature of the FPGA Xilinx system generator implementation. So need not be a HDL expert. If they have just the knowledge of architecture and how to build that architecture, that becomes an advantage for everyone. Once again, I thank the head of the department, Professor Uday Kumar sir, and Dr. Sindhuri, and other faculty members. In fact, I feel very honored to have me for this presentation, as I am being an alumnus of this particular college. So once again, thank you very much, sir, for giving me this opportunity, for the management and for the head of the department, and for all the faculty members. Thank you.